Alright guys, let's kick things off with particle swarm optimization, or PSO. Think of a flock of birds searching for food. Each bird is a potential solution. In a way, each one is trying to find the absolute lowest point in the fitness space. Now, PSO imitates this behavior. Each bird adjusts its position in the search space according to its own best find. Its personal best, and of course, it's influenced by the overall best finding of the entire flock, the global best. It's a beautiful dance of intelligent cooperation, leading to a super efficient way of finding the absolute best solution. Think about optimizing the control parameters of a DC motor to spin at precisely the right speed. That's where PSO shines. Or imagine fine-tuning the parameters of a liquid-level system in an industrial process that demands near-perfect precision. These scenarios get super efficient with PSO. The amazing thing is that many similar scenarios get improved with it. The efficiency comes from the fact that PSO finds a very good solution with fewer iterations than similar methods. This makes it a very popular amongst many people and has been used in many fields. See how it's applied in power system control, ensuring super stable and efficient generation distribution networks. The optimization process for electrical energy systems has been. The visualizer below beautifully shows this process. Next up, genetic algorithms, or GAs. This one mimics the marvel of natural selection, the survival of the fittest. Imagine a population of potential solutions coded to resemble chromosomes. Over successive generations, better solutions survive and reproduce, while weaker ones get weeded out. It's a continuous process of refinement. Crossover mixes the best genes from different individuals, while mutation introduces random variations. It's like nature's very own design process, which is amazing. Now, think about optimizing complex logistical issues like route planning for efficient transportation in a complex industrial environment. It has been used to provide a solution for this type of work by finding the most efficient delivery route and minimizing fuel consumption, time and costs, maximizing profits, and minimizing environmental damage. GAs are ideally suited here. Similarly, GAs play a crucial role in high-efficiency production planning and manufacturing. GAs help build optimal production schedules, arranging tasks to utilize factory machinery effectively and reduce wasted time, and ensure efficient work through a plan that is based on data. As such, GAs boost productivity while enhancing resource management and lowering expenses. Check out this amazing visualization to see this process. Let's move on to the Gray Wolf Optimizer, or GWO. This algorithm mimics the impressive hunting strategies of wolf packs. Imagine a hierarchy. Alpha, beta, and delta wolves lead the pack, guiding the search for optimal solutions. Isn't this amazing? The other wolves follow, and they all adapt and learn by watching. It's a beautiful thing that nature's wisdom teaches us. GWO is excellent for many different applications where optimization is required. Take the task of optimizing the control parameters for a 3-tank liquid-level system in an industrial setting. Accurate management is critical, and GWO does a phenomenal job of doing this. The visualization below will impress you on many scenarios. Similarly, GWO demonstrates outstanding capabilities for optimizing parameters within machine learning models, improving accuracy and speed. The improvement in precision, speeds, and overall effectiveness of parameters of the machine learning approach has created important and timely opportunities across many different fields. Applications for these types of optimization range enormously from healthcare to agriculture. Check out just a few illustrative examples. The visualizer below wonderfully depicts this procedure. Now, let's broaden our perspective to take in metaheuristic algorithms in general. These algorithms are not confined to a single technique, but are instead nature-inspired, which provide powerful, flexible ways to solve optimization challenges. They're based on principles from biology, physics, sociology, or even human decision-making. And these algorithms aren't just theoretical. They're used to solve some of the most complex engineering problems. Think of the design of large-scale offshore microenergy systems. Efficient operation, that's where these algorithms become indispensable. Through balancing operational costs, minimizing carbon emissions, maximizing energy efficiency, and mitigating risks associated with unpredictable energy fluctuations, they're doing a phenomenal job. Take the design of high-permeance seawater reverse osmosis systems. Optimizing these multi-scale systems that requires complex models and high-fidelity calculations to be done computationally, metaheuristic algorithms like these are needed here. Check out this visualizer to see their potential. The applications of these algorithms are even more mind-boggling, ranging enormously from the design of graphene-based plasmonic enhanced photodetectors to autonomous vehicles path planning when facing real-time threats. Often, Combining the strengths of different techniques leads to even better results, and that's what we call hybrid optimization. It's brilliant. You can combine particle swarm optimization with genetic algorithms, or gray wolf optimizers with cuckoo search, or any number of other combinations. It's like getting the best of several worlds. Let's take a look at a compelling example, a new hybrid optimization system termed Hycopso. This method combines the agile movements of mountain gazelles with the exploration of particle swarm optimization for better control systems of multiple microgrids. In complex power grids, achieving optimized and coordinated control between multiple microgrids demands advanced optimization techniques. By optimizing the PI controller parameters, this new system has the ability to improve the efficiency and adaptability of hierarchical control systems. It not only ensures equitable power sharing but also maintains voltage and frequency stability, which ultimately leads to more efficient and more dependable power networks. The visualizer below shows many similar situations of how these algorithms are used for. Now, let's talk about the real-world impact of these AI optimization algorithms. They're not just theoretical concepts. They're used in a shocking number of applications. They're revolutionizing various industries, from energy to medicine to finance. In the energy sector, they're optimizing economic and emission load dispatch for power systems, making energy production both more cost-effective and environmentally sound. In medicine, they're enhancing medical image classification. To improve diagnostics in medical fields using these advanced tools, highly advanced strategies were applied and the efficacy of these techniques are shown. It also improves diagnostic accuracy and prompt clinical interventions. Let's take a look at a few more compelling examples of how they are applied in different fields. The application in finance is another striking instance. They're helping refine portfolio selection strategies to reduce risks and increase returns. These algorithms aid in optimizing resource use as well as making investment decisions. It reduces costs and enhances the quality of services and products produced as well. Take a look at this visualizer to see how they are applied in various industries. They're instrumental in many more areas ranging from optimizing task scheduling and fog computing for big data applications to reconfiguration of low-voltage distributed power systems. See how these algorithms work behind the scenes and are influencing our lives. The future of AI optimization algorithms looks incredibly bright. As computing power increases and data availability expands, we can expect even more sophisticated algorithms to be developed. We'll see an increasingly prominent role played by these algorithms in addressing the world's most complex challenges. Think of their potential in climate modeling, drug discovery, material science, and sustainable development. The ability to tackle high-dimensional, complex problems and refine model parameters dramatically increases performance levels as well as speeds. Moreover, advances in computer science that are based on quantum and supercomputing techniques will drastically improve the speed and efficiency of these algorithms. This will open up even more amazing possibilities for solving complex problems. The integration of AI optimization techniques with simulation data and mathematical models is expected to unlock more efficient and practical tools. The use of these methods might not only advance technology, but also offer various other benefits, ranging from improving living standards to environmental sustainability. It is likely that these algorithms will be integrated frequently in conjunction with various other models, such as neural networks, to improve the accuracy and efficiency of predictions for all kinds of diverse and complex problems. Just imagine the possibilities. Check out this visual below for more of the exciting possibilities.